I'll be presenting a startup. We started with Professor Andy Schwartz and myself that is called ThinkLink. And the idea is to connect brains to the world as it's written here. And I'll tell you more about it. So, oops. So in many pathologies and people's brain work perfectly. And unfortunately, the spinal cord might be destructed or sometimes you can't speak anymore. There are many pathologies where it would be really, truly interesting to connect to a brain, understand the intention of the person who cannot execute something, and try to execute it right. So this idea of decoding intention can have a wide range of applications because if people cannot speak, we can understand from their brain activity what they want to say and say it for them. Like Stephen Hawking used to do it himself, you know, he would follow letters and create words. But you can also allow people who are tetraplegic or paraplegic to control arms so they can live again, scratch themselves, do elementary things and much more advanced things like maybe control an exoskeleton, maybe when they allow you to drive. So this idea of reading intention and perhaps also writing information to portions of the brain that are not connected anymore is really what we want to be doing and what we're doing for the last 15 years. So what is our product? Our product is to develop a small chip that you can put in somebody's head following all the NIH and all the FDA approval lines of development to be able to connect to an area that is not functioning or is not connected anymore to what we want to be doing and decode intention. And that can only be done properly if you have to, I mean, by being invasive. It means you have to go under the skull, put one time this little chip there that will start streaming to the outside world, as you can see here. And then you can have a small computer that computes what you want to do. For example, if you want to drive your car, it will decode and then you start steering the wheel. If you want to control a robotic arm, it's the same. So this is a product and I've developed many of these to restore vision for blind people, 2 generations that went to successful trial and also created 2 startups on this technology. The hardest thing here is to make it survive by being in a human body. And the second thing is to make it simple to use and simple to implant. So any doctor in the world can do it without heavy machinery and without failing it, because we're talking about human lives and human dignity. And so what we've done is many people around the world, and Andy is a world leader in this kind of technology, have massive pieces of technology that are not meant to be implanted in a human being and used on a daily basis. So as you can see here, you have huge racks, huge connectors I will show you later. And the idea is to shrink it all and make it very small with this new technology that I'll be showing you. So what makes us unique is, I mean, you hear about Elon Musk doing this. Elon Musk is using what Andy has developed and like many people in the world. But in this breakthrough we've done lately here in Pittsburgh was to introduce and use technology for something called Neuromorphic, which means it's a branch of engineering where we copy brains to build hardware. And this was initiated in the US at Caltech in the 90s by Professor Carver Mead, who is the father of all electronics, I mean, the one we use today. And that led to many development and to which I belong. This is my field. So the idea is always to copy brains and then you end up, for example, here we copied a retina, a silicon retina and built one. And this one was used to restore vision for blind people. So the advantage of copying brains is that you are really speaking the language of brains. So you easily interact and compute. It's also very low power. Brains burn 20 watts a day. And it also has many advantages in terms of computation. You don't need lots of batteries. The computation requires very few energy. And so it has many advantages. And most of all, what allows us to be above everybody is that this technology allows you to have an infinite or a limited number of electrodes. You can put thousands, hundreds of thousands, whereas most of the existing technology will go hardly beyond 200, 1,000, really maximum. And that is not enough because you won't have enough information.
Thanks, Benjamin. That was very interesting. My question has to do with other ways, or you might call it even competition to this approach, because it sounds like you're opening somebody's brain and implanting something. And if somebody's blind and would be able to restore their vision, I can see why they might take that risk. I'm just wondering what you see as the competition for this approach, for the kinds of things you're talking about, like scratching your back or asking for something. Are there other approaches people are using that don't involve opening your brain?
Sure. For now, you need a caretaker that costs thousands of dollars a month, and that's the best option you have. Otherwise, technology-wise, you can hear about EEG, but EEG are very sloppy because you're above the skull and you don't know what's really happening to you. So you can't really decode. The only way to restore and give, back, motion to people and is to allow to go in under the skull. So just to let you know, when we design such a system, the scope is to make the surgery as fast as possible, as non-invasive as possible, and easy to be done. Because if you design a very complicated product, it won't work because people won't be able to implant it. So all those parameters.
Have to open their skull, right?
Yeah, but today people do it on a daily basis. If you go to the hospital here, people who have epilepsy, if they put the electrode, they stay in the hospital for a day. So we're talking about like a small, I count in centimeter, I'm sorry. We're counting about few centimeters. So it's really, I would say it's a surgeon, any surgeon can do this surgery. It's not very complicated. Yeah.
Thank you.
We're not removing all of it. It's no. Yeah.
Hi, Benjamin.
Hi.
Hi. So you mentioned very briefly the FDA and probably some regulatory things that have to go along with this, obviously so, right? So can you tell me what national medical regulations or approvals you would need for something like this? And if you do, how far are you along in that process? Like, have you all already gotten those permissions?
Okay, so we are starting the company in the sense that we are looking for investors, and we have a few we are thinking of, and it's the situation is not very good at the moment with COVID. So when you design such a product to become medical grade, you have to follow very strict rules from day one. You don't develop such a device and then think about it. You do it from day one. And so I have lots of experience in that. I've developed three generations. And normally you have a path where you, for example, you log everything you do on a daily basis following very strict protocol. And then you apply that to do a clinical trial. And to do a clinical trial, you have to have shown that your system can live inside the human body for a certain amount of time and that it's operating correctly. And normally you do that on pigs or small animals, just to show, look, I don't know if it's working, but I put it there and it's still responding and it's still working. That's all we need to do. And once we know that is working, it means your system is safe to be put in a human being. And then you, as you could see maybe in the video, the monkey could really move an arm because monkeys are smart. But we have also done it on humans here in Pittsburgh, and Obama came and because he funded the project with the Obama Brain Project Initiative. So we can make it work. Now the question is, can we make it work in 1 centimeter? The question is yes, of course. It just requires money and energy and passion. You don't do this for the money. You do this because, as a scientist, when I made my first system for blind people work and I went to the hospital and we saw it implanted on a human being and it's a life, it's a family around it. And the day you turn it off, it's something you can never forget. So you can mess with these kind of things. You have to follow very, very strict protocols.
Benjamin, thank you very much for a very, very interesting presentation. I guess one of the questions I have, you're right, it's not about money, but at the end of the day, you are creating this not just for the benefit of humans, but also for helping as many people as you can. So how large do you estimate the market to be of people afflicted with some kind of paralysis or ailment that would require this?
So we looked at the costs today that we can reduce and all the pathologies, and we estimate it to be around 17 billion today. And you can just by tackling paralysis and reducing caregiver costs, and also you know, many other fields. I would say, yeah, it's a 17 billion market just for moving an arm. So that's the product, right? First one. But then you can expand to many other products. For example, people who cannot speak anymore, you can make it speak. But then also there is a lots of things to be developed for. It's even more $1 billion to allow people to control things in their house or control a computer. Because what you have not seen is that once you put this system on a human being and he starts controlling an arm and says hi, it becomes, it's like you when you play tennis or you play tennis table, that racket becomes part of you. So people really start to feel that the robotic arm is part of their body.